Look at the horizontal glow bar on the lid of this laptop. While it might look like a battery indicator or a message alert, Google designed it for a specific technical purpose. The purple light signals that the system is currently executing an action it initiated itself. It is a physical marker of the machine moving from a reactive state to an autonomous one. For 15 years, the industry narrative suggested that the cloud was sufficient. We were told that a browser could serve as a complete operating system, and that waiting for a loading spinner was simply the price of a simplified user experience. Behind that narrative, Google's kernel team was working on the Dead Sea build. They froze their legacy Linux code and spent 18 months redesigning the operating system from the ground up to support local AI inference. The result is the Googlebook. It replaces the Chromebook with a native Android stack designed to run AI models directly on the device hardware without requesting permission from a remote server. Chromebooks pay a translation tax. Apps run in virtual containers, converted by a middle layer, adding a 200 millisecond delay per operation. The Googlebook removes this using the unified neural layer. NPU, CPU, and memory speak the same native language, moving data without emulation. By removing the cloud connection and the translation delays, the machine stops waiting for external instructions. The speed of the hardware has finally caught up to the speed of human thought. Standard laptops use context switching to manage tasks. When you have 50 tabs open, the CPU isn't running them all simultaneously. It's jumping between them thousands of times per second. This constant switching generates heat and causes microstutters. The Googlebook's Wildcat Lake NPU provides 40 trillion operations per second of dedicated power. It doesn't share these resources with your browser or your spreadsheets. Its only function is to predict. This predictive power is most visible in the Magic pointer, which changes the way the system interprets your physical movements. When you move the mouse, the NPU analyzes your velocity and trajectory as kinematic data to determine where you intend to go. Before your finger reaches its destination, the system pre-renders the target UI state. You are confirming a destination the computer already prepared. This speed enables features like the couch mashup. While a desktop workstation might take nearly a minute to calculate physics-based lighting for a 3D object, the Googlebook does it as fast as you can drag your finger across the screen. When the machine computes faster than you can move, it crosses a threshold. It stops being a tool that reacts to your commands and becomes a system that anticipates them. There is a physical cost to this constant prediction. Running maximum AI loads generates significant heat within the silicon. Most laptops manage this by throttling or slowing down the chip's clock speed once it hits 95 degrees. This prevents damage, but it also slashes the performance you actually paid for. The Googlebook avoids this slowdown by using a protocol called the thermal mesh. When the laptop hits its thermal limit, it initiates a peer-to-peer handoff, identifying idle NPU cycles on your nearby Android phone and offloading processing work. By distributing the workload, your phone becomes an external processor, allowing the Googlebook to maintain peak performance without throttling. This mesh requires the laptop to maintain deep, persistent access to your phone's internal state. It has to monitor your location, your network connection, and your active app data to ensure the handoff is seamless. Your devices have merged into a single computational unit. This happens automatically, operating in the background without requiring a separate prompt for every connection. The unified neural layer, the Magic pointer, and the thermal mesh are the technical components required for the computer to function independently of human instruction. For the first time, we are using a machine that does not sit idle while waiting for us to tell it what to do. The left click used to mark the beginning of an action. On this device, it's merely the final confirmation of an action the system has already staged. If the machine correctly prepares your destination before you even arrive, it raises a question about the nature of the interaction. At what point does the computer's prediction begin to influence the user's choice?